In previous videos, you've seen the properties of concave and convex mirrors and their applications. But based on their shape, people usually talk about two types of mirrors, parabolic mirrors and spherical mirrors. So in this video, we'll explore what these are and where they are used. So if you want to build, say, a concave mirror, which can focus all the parallel rays of light to a single point, then the shape needed is called as a parabola. And such mirrors are called as parabolic mirrors. And if you're not too sure about what this parabola means, don't worry too much about that. It's just a name that we give to this particular shape. So in general, parabolic mirrors are mirrors which are part of a parabola. You can make it a big part of a parabola, or you can make it a small part of a parabola, but it has to be a part of a parabola. And by the way, we are seeing a concave mirror here, but the same thing applies even for convex mirrors. Now, here's the thing. Building this parabolic shape is a little bit hard. Because you see, if you look at this shape carefully, notice right at this point, we can call this as the tip of the parabola. Now, right at this point, you can see that we have a nice curve over here. But as you go farther and farther away from this tip, for example, if you look at this part, it's pretty flat over here. Can you see that as you go farther away? So close to the tip, it has to be curved, and then the farther you go, the more flat it should become. And that's a peculiar shape, and getting that shape exact is pretty hard. But do you know which is the easiest shape to build accurately? I'm pretty sure you can guess it. A circle. But to be more accurate, in 3 dimensions, a sphere or a round ball. And that brings us to spherical mirrors. Spherical mirrors are mirrors which are parts of a sphere. So spherical mirrors, these are called as spherical mirrors, and they are parts of a sphere. And since spheres are the easiest to build, spherical mirrors are also easy to build. But here's the thing, we just saw that parabolic shape is what is needed to focus all parallel rays of light to a single point. So what happens over here? Well, let's throw parallel rays and see what happens. We clearly see that the rays of light are not getting focused at a single point. And that shouldn't be too surprising because we've already discussed that the only shape that can do that are parabolas. So obviously anything other than parabola, like a sphere, will not be able to focus the parallel rays of light to a single point. So a valid question could be, then why do we build this? Because they are not focusing rays of light to a single point. Well, here's the reason why. If you look at these rays carefully, then you see it's these extreme rays of light, the rays of light which are very far away near the edge over here, it's these rays of light which are the culprit for not being able to focus at a single point. Here, let me change the color of that and you can see it better. There it is. You can see it's these extreme rays of light which are actually making that spot spread. And so one solution is just get rid of these rays of light. And the way we can do that is just by chopping this part of the mirror. So let's chop that mirror and see what happens. And now we see that that spot has become sharper than before because we got rid of those extra rays. Sure, now that we are receiving less amount of light, it is not as bright as before, but it's sharper than before. And we can now guess to make it even more sharp, well, we have to chop more part of that mirror. So let's do that. And you clearly see that now almost the rays of light are clearly being focused at a single point. So we can conclude that as long as we build a spherical mirror such that it forms a very tiny part of a sphere, then it'll be approximately able to focus all parallel rays to a single point. And if you're wondering why is this working out so well for us? Well, that's because when you take a small part of this sphere, then it nicely matches up with this small part of a parabola. Let me just keep this on top of that and show you. So if we take this tiny spherical mirror and we try to keep it on this parabola, notice that it pretty much matches up. This curve, this tiny part pretty much matches up with the parabola. And that's why it's able to behave like a parabola and able to focus all parallel rays of light. But if you take the large part of a sphere, then you can see, and by the way, this is not so accurate, but you can pretty much see that the two shapes now don't line up anymore. And so long story short, if we don't care too much about the accuracy and we're fine with having tiny mirrors, then we can use spherical mirrors, mirrors which are parts of a sphere. They are easier to build, and as a result, they are cheaper and more readily available, which is perfect for educational purposes, and that's why you probably use them in labs. On the other hand, if we want to build a giant astronomical telescope for scientific purposes, where we want to look at extremely far away galaxies and stars, then we would want a mirror which is as accurate as possible and a large piece of a mirror. In such cases, if the budget is not an issue, money is not an issue, then we'll go for parabolic mirrors.